This video is presented to you by www.testprepadda.com. Dear students, in the previous session of General Organic Chemistry, I started the discussion of carbocation. I talked about the stability of carbocation there. I took many examples and checked the stability of those carbocations. Here also I will take a few special examples of carbocations like the carbocation where positively charged carbon is attached with heteroatom having unshared pair of electrons. I will talk about non-classical carbocation such as cyclopropyl methyl carbocation. I will talk about the case where because of positive charge carbocation becomes aromatic and due to that stability increases. First of all, I'll take this example R C R plus O CH3. Now here you can see this positively charged carbon is attached with heteroatom having unshared pair of electrons. These heteroatoms can be oxygen, nitrogen, halogen, etc. My point is clear. Now here what is happening? This is having empty orbitals. So this is empty orbital and here this oxygen has the filled orbital. So this delocalization takes place and because of this stability increases. If I write the resonating structure, it will be like this here. My point is clear. And because of this direct delocalization, the stability of this type of carbocation is more than tertiary carbocation and more than benzyl carbocation. My point is clear. So whenever you find such type of carbocations, their stability will be more. My point is clear. Now students, let me tell you, simple acyl ketones are also stable. Like if I write RCO plus, this acyl carbocation is as stable as a tertiary butyl carbocation. Tertiary butyl carbocation is CH3 whole thrice C plus. And if I write the resonating structures here, it will be like this. RC triple bond O plus. So these are the resonating structures of acyl ketones. So acyl ketones are also stable and as stable as tertiary butyl cation. Now consider these two examples. CH3O CH2 plus CH3 NH CH2 plus. In both the cases, you can see this positively charged carbon is attached with heteroatom having unshared pair of electrons. So in both the cases, direct delocalization. But what is happening? If I write the resonating structure of this, oxygen gets positive charge. If I write the resonating structure of this, then nitrogen gets the positive charge. And let me tell you, more electronegative element is less capable of holding positive charge. That is why when you compare the stability of this carbocation with the stability of this carbocation, the stability order will be written as this. My point is clear? Now I'll take another example here. If I take this, in this case, what is happening? This positive charge is delocalized here. because it is plus single double. But this is not the normal resonance case. What is happening? Because of this delocalization, you can see we get a loop of 6 pi electrons, and that is Huckel's rule. And this way, this carbocation becomes what? Aromatic. So this positive charge is responsible for the aromaticity of this carbocation. That is why its stability will be very high. Its stability will be more than the case where carbocation has the heteroatom having unshared pair of electrons, will be more stable than the tertiary carbocation, will be more stable than the benzyl carbocation. My point is clear. So aromaticity provides extra stability to carbocation. Now I will talk about the cyclopropyl methyl carbocation. This is cyclopropyl methyl carbocation. Now, if I ask you what is the hybridization of this carbon, you will say sp3. What is the hybridization of this carbon? You will say sp3. What is the hybridization of this carbon? You will say sp3. And what is the bond angle here? You can see 60 degree. It is simple. It is simple. It is simple equilateral triangles. You can say 60 degree. Now, for sp3, what should be the bond angle? 109 degree 28 minutes. You can see so much of deviation is there. Means ring is highly strained. Ring is highly strained. Normally what happens when you form a single bond? There is overlapping of orbitals like this. Overlapping of orbitals. This is normal axial overlapping. But here what is happening? Because of strain, the orbitals become like this. Bent orbitals. Bent orbitals. Bent orbitals means now it is like this, and here this is the positive charge carbon, and this is the vacant p orbital, and here these are the bent orbitals. Let me tell you that this vacant p orbital lies parallel to these bent orbitals. So this results in the conjugation between bent orbitals of cyclopropyl ring and vacant p orbital of cationic carbon, and due to which stability increases. Here stability increases. So bent orbitals are responsible for the increase in the stability. Are you getting my point? Now, this stability is so high that this is even more stable than tertiary carbocation as well as benzyl carbocation, but it is less stable than the case where carbocation is attached with heteroatom having unshared pair of electrons. My point is clear. Now, more the cyclopropyl ring attached with this positive carbon, more will be the stability. For example, if I write this is more stable than this, will be more stable than this. So what is happening here in this non-classical carbocation? Here the delocalization is there, or this dispersion of positive charge is because of this single bond. This participates in the delocalization process. So I can write this as plus will come here. Similarly, another possibility is like this. Here, in this situation, I will get like this. Plus will come here. That is why sometimes it is also referred as dancing resonance. Dear students, let me tell you that for others like cyclobutyl, stability is found as ordinary as alkyl groups. Now let me summarize whatever we discussed for the stability of carbocations. Here let me take the example like this. Double here, double here, double here. This is aromatic. This is aromatic carbocation. That is why this will be the most stable. Then I can write CH3O CH2 plus. Its stability is because of presence of heteroatom adjacent to carbocation and direct delocalization. It will be more stable than the cyclopropyl methyl carbocation, and it will be more stable than the tertiary carbocation. It is more stable than the benzyl carbocation. It is more stable than the secondary carbocation, more stable than the primary carbocation. My point is clear. In all these cases, like here, if I increase the number of cyclopropyl rings, the stability increases. Here also, if I increase the phenyl rings, then the stability will increase. Dear students, this is all about the stability of different carbocations. In the next video lecture, I will talk about the carbon ion structure and stability. Thank you. This video is presented to you by www.testprepadda.com. TestPrepAdda.com provides free audio-visual lectures of different subjects by expert faculties, free online tests prepared by expert faculties to students who are preparing for engineering or medical entrance exams or planning to take exams like KVPY, Olympiad, etc. It provides a platform where students can interact with mentors to improve their performance in the exams. The mission of this online medium is to help students to achieve their goals. Log on to www.testprepadda.com to watch free video lectures on different topics, to download free revision notes, to take free chapter-wise online tests, progressive test, and mock test, to discuss doubts with mentors. Thank you for watching the video. To stay up to date with the latest videos, subscribe to our YouTube channel. Like us on our Facebook page, Test Prep Adda. All the best.